Kia ora Year 12. Here's question 2 from the second batch of practice questions for the Trig internal next week. So this one is pretty similar to the ones in question 1, probably a little bit harder once we get into it. So again, we're given two functions, but it's set up slightly differently. You have to figure out what's being asked here. So we've got the first function is this one, and the second one is this one. So this g of x function is pretty straightforward to visualize, right? So if you think about sine of 2x, it just looks like this. So it's a sped up sine function with a period of pi instead of 2 pi. So that's my pi marker there. And it's negative 2 sine 2x, so it's reflected in the x-axis, so it's upside down sine curve, and it's got an amplitude of 2. So it's going to start here. Let's just draw it out. So it's going to look like this. Very bad drawing, but you get the idea. So this value down here will be negative 2. This one up here will be 2. So that's what we're going to have on one side. Now this one here is a really cool function. I've done that in GeoGebra. So it's a sine squared plus a sine of x. So it's not an ordinary sinusoidal thing. It looks like this. Okay, so this has got sine squared of x plus sine of x. And so we're being asked to say when will those two functions intersect. So here's the graph with both of them on. Now I'm going to show you this before we do all of the trig work so that you can get a feel for what the solutions are going to look like. Well, you can see on here that we've got some pretty cool patterns. We can see that the green, the orange and the blue curves intersect at multiples of pi, and it looks like they intersect at some multiples of pi on 2. So that's negative pi on 2 there, that's pi on 2 there, that's 3 pi on 2 there. They don't intersect here, which is kind of weird, but that's okay. So we're going to see that coming out. But then on top of that, we've got points like A and H, which is just, strange intersection points. Not possibly multiples of pi, but possibly not. So let's go and do some algebra to see what's going on. So we've got sine squared of x plus sine of x is equal to negative 2 sine 2x. So the obvious first step here is to deal with the double angle. And I'm going to pull everything over to the left-hand side at the same time. So I'm going to have plus 4 sine x cos x equals 0. Now if you look at that, you can spot that you've got a common factor of sine x. So let's factorize that. That leaves me with sine x times sine of x plus 1 plus 4 cos of x is equal to 0. So this bit is good. Sine of x equals 0. This bit is not so good. So I'm going to rewrite this. Well, let's just start by writing it like this and then we'll have a look. Sine of x plus 4 cos of x plus 1 is equal to 0. So we have to think about this one. This one here, though, we can finish off straight away. The general solution for sine of x equals 0, well, we can do it using our usual alpha formula, or we can just do it by using our brains and the graph. So we end up here with x is equal to m pi. It really couldn't get much cleaner. And if you go back to that graph, you can see that that's the multiples of pi that we had. Okay, what are we going to do with this? Well, one thing that we might try is not trying to factorize and have something equal to 0. Instead, we might do this. Sine of x plus 4 cos of x is equal to negative 1. Okay. If I square it, I'm going to be able to use the Pythagoras identity and have some leftover stuff. So let's see what happens when we do that. We're going to get sine squared x plus 16 cos squared x plus 8, let's see, 8 sine x cos x is equal to 1. That'll give me sine squared x plus cos squared x plus 15 more cos squared x plus 8 sine x cos x is equal to 1. So why did I split this up into the 2 bits? Well, it was because I could see here that I had 1, and I could see here that I could get 1 and some leftover out of this. So that leaves me with 1 plus 15 cos squared x plus 8 sine x cos x is equal to 1. And now we're getting somewhere because we can factorise. So cos of x times 15 cos of x plus 8 sine x is equal to 0. That gives me cos of x is equal to 0, or 15 cos x equals negative 8 sine x. Sine x over cos x. Be careful with this, which way we're going. Well, we're going to have negative 15 over 8. So tan of x is equal to negative 15 over 8. Alright, so now from here it should be pretty easy. So this is tan of x is equal to negative 1.875. Alpha is equal to the angle whose tan is that. And that comes out as negative 1.0808. I think I'm just going to cheat and check my spreadsheet with all my calculations. Yep, that makes sense. Okay, and that fits with my tan graph, right? So we're looking at somewhere down about here. And the general solution for that, because this is just x, is a straightforward x equals n pi minus 1.0808, and then we can chuck values in there. So we're getting one lot of solutions from that, and then in here we're going to get solutions of, so alpha is equal to pi on 2. Skipped a tiny step there. There's my cosine graph. So the principal value that will give me 0 for a cosine is pi on 2. So my general solutions are 2n pi plus or minus pi on 2. Okay, so we've got 3 of those. So 3 equations working out there. We've got x is equal to n pi, or x is equal to 2n pi plus or minus pi on 2, and then this one here. What would be a good thing to do though is, and I haven't got time to do it now, but we should really go back and check that all of those values are valid. So I often get a bit nervous when I'm squaring things, whether I'm going to get any false solutions popping in. So if I were actually doing that one in the internal, I would go on and do that. I'd do a table and I'd do some particular solutions, right? I'd take values for n, and I'd get those numbers out, and then I'd go all the way back up and plug them into f of x and plug them into g of x to check. Because if you look at that graph, the thing that's making me not satisfied that all of those are going to be valid is that the weird points like the h and the a don't seem to be. Let's just have a look. Now the h and the a points are okay, but here I've got negative pi, so the multiples of pi are definitely good, and they came from x equals n pi. But the last of the general solutions was x equals 2n pi plus or minus pi on 2. So 2n pi minus pi on 2 gets me this one, and then but 2n pi plus pi on 2. Anyway, that's all for now. It's wildly unsatisfying end of this video, but go away and check whether what comes out of the general solutions actually works in those equations, because when you look at going all the way back here, we might have introduced some invalid false solutions. Thanks for watching. Please leave me any comments if there's any mistakes. I've done this one in quite a rush this afternoon, so there could be problems with it. Just let me know.